Hello, good afternoon, everyone. This is Lin Chen from Texas Tech University. And in this talk, I will be talking about new bounds on augmenting steps of block-structured integer programs. This is a joint work with Martin Kotechi, Lei Zhu, and Weidong Shi. Okay, so let's start. Let's start with the general integer program, so here I just write the standard form for an integer programming where we want to minimize or maximize a linear function subject to the constraint, where the constraint is written as hx equals to b, where h is the constraint matrix, and we have the lower and upper bound for the integral variables x. And here, by talking about block-structured integer program, I mean the constraint matrix H has a block structure. And what is exactly a block structure? So I will be providing you with several examples later, but at the beginning, let me just be straightforward. So throughout this talk and also the paper, we will be focusing explicitly on this kind of block structure where H consists of one copy of a small submatrices C and n copies of small submatrices A, B, and D. As you can see here, that the first row contains one C and n copies of D, and the diagonal consists of one C and n copies of A, and the first column consists of one C and n copies of B. Okay. So the first question, of course, is, why are we interested in block structured integer program in general? And what in particular, so why are we interested in this specific kind of block structured integer program, which we call it as full block n-fold integer program? So let me use one of my favorite optimization problem scheduling to illustrate you to demonstrate the modeling power of such kind of block structured integer program. So indeed, this could be a very general, a unified modeling tool for a variety of optimization problems. And here I'm just using scheduling to give you a little bit idea. So let's consider the standard scheduling problem where we are given a bunch of jobs. So here, so I use rectangles of different color to represent jobs, and the length of the rectangle represents the processing time of the job. So each job, we also have a bunch of machines, and each job has to be processed continuously on one of the machines. And the goal is to assign jobs to machines so that a certain objective is optimized. And here, for simplicity, let's just focus on makespan, okay? One of the most popular objective, where makespan refers to the earliest point in time when you finish all the jobs. As you can see here, the red job is the job that finishes the last. So it's the time when we finish all the jobs, and this would be the makespan, okay? So let's formalize the problem. So we are given nj jobs of processing time pj, and the goal is to find an assignment of jobs to machines so that the makespan is minimized. And of course, we know that using the standard technique, we can instead ask for the determined problem whether it is possible to schedule all the jobs within some targeted makespan t. And then later on, we can, if we have this algorithm, we can simply do a binary search on t to find out the minimal t. So for this determined problem, indeed, actually, so it's not difficult to come up a natural integer program for this. So if we let xij be the number of jobs of processing time pj, that is scheduled on machine I, then we can come up with the following natural integer program. So as you can see here, the first set of constraints tell you that, well, the total number of jobs of processing time Pj, if you take into account of them among all the machines, they must equal to the total number of the jobs you have, which is Nj. And the second set of constraints basically says that if you consider the total processing time of jobs scheduled on machine I, it should be at most T. Okay, so this is kind of the most straightforward way of establishing an integer program. And the interesting thing is that, well, indeed, this is a nice observation by Knott and others, you know. It's very interesting that if you just, you know, take a little bit time and rewrite the whole constraints into a constraint matrix, you will realize that very interesting that the constraint matrix actually has such a structure as you can see here. The constraint matrix H, if you look at it, the first rows corresponding to the first set of constraints is actually, you know, all identity matrices. And then you have the second set of constraints, which correspond to the yellow box where you diagonally you have this vector P, where vector P is simply a vector of job processing times. Okay, so it's kind of, you know, straightforward if you just write down the constraints in a more systematic way. And if you look at this constraint H and compare it with the full block n-fold integer program I told you in the very beginning of this talk, you will see that this is actually a special case where we have C and B, the first column all set to be 0. Okay, so this is kind of a special case. But it's kind of interesting, as you can see, that block structured integer program can indeed be used to model a variety of such kind of problems. And of course, you might ask, so what's the advantage of such kind of modeling? Well, so one straightforward result that directly follows as, you know, once you have such a modeling is that you can immediately apply the algorithm for block structured integer program and derive an algorithm for scheduling, for example. And the best known algorithm for n-fold, you know, this is called n-fold, the special case of full block n-fold. So if you apply the best known algorithm for this, you immediately obtain the approximation algorithm and FPT algorithms for scheduling problem that, you know, meet the current, you know, algorithms for this, which is kind of, you know, interesting because now you don't need to spend a lot of effort, but you just derive it straightforwardly. And of course, if you are considering a new problem, you immediately get an algorithm for that, which is interesting, of course. And of course, so this is just a special case. And let me further point out that what is the relationship furthermore with the full block n-fold we are considering. So indeed, so let's think about a very natural problem. Let's just take one step further about the scheduling problem by asking ourselves, what if T, the target make span, is no longer a fixed value, but rather a variable? I mean, in this case, definitely the constraint matrix becomes more complicated. And the reason here T is not a variable is because we can do binary search. But if we cannot do a binary search, then things becomes tricky. And let's consider the following, the almost a directly generalization of the scheduling problem, which is scheduling with job rejection. So let's say again, so we have Nj jobs of processing time Pj, and in addition to that, we also have a rejection cost Cj for each kind of jobs. Okay, so this means that by paying a cost of Cj, you can remove one job, Pj, from your job set. And now the goal is to find out a schedule that minimizes the total cost, where the total cost is defined to be the make span plus the total rejection cost, okay? So that's a kind of a straightforward generalization of the scheduling problem, which has studied, you know, also in the scheduling community, scheduling with job rejection. And now let's introduce, I mean, to model this problem, let's just introduce natural variables y of j to represent the number of jobs of processing time pj that we reject, okay? And now a straightforward formulation gives us, you know, this kind of constraint where the first set of constraints, the total number of jobs is no longer nj, but nj minus yj. Okay, but everything just follows directly. And remember that here, we can no longer do a binary search on T. And also, as you know, that T, there are, you know, pseudo-polynomially number of different kind of values for T. So definitely we cannot enumerate that, and we have to let it be a variable. And once T becomes a variable, as we can see here, and if you further write down the constraint matrix, you immediately end up in the constraint matrix, as you can see on the right side. And you can see that this essentially, you know, falls as a one kind of, you know, as the 4-block n-fold integer program, okay? So now you can see that this is really very naturally that just arises from a lot of optimization problems. So hopefully I have given you one example, and as I would like to emphasize that, you know, I just give you an example of scheduling, but indeed, such kind of block-structured integer program arises in a variety of problems that has been studied by researchers in recent years, including scheduling, multi-strings matching, fair allocation, you know, like multiple TSP on the tree, etc. And and think about it. So, you know, if we have a good algorithm for a block structured integer program, it means we have a sharper tool for all of them. And any improvement on such kind of integer program gives us a simultaneously improvement on the algorithms for a variety of these kind of problems. So I hope at this moment, I have provided you with, you know, sufficient motivations for studying these kind of integer program. And now let me talk about the related work. Again, so let me just, you know, draw attention to this 4-block n-fold integer program, which is kind of the focus of this talk, okay? And so together with this, let me also mention a little bit about other kind of block structured integer program, which is known as n-fold and 2-stage stochastic. And as you can see directly from this, you know, constraint matrix, you can see that n-fold and 2-stage stochastic are just special cases of 4-block n-fold, where you set either C and B to 0 or C and D to 0. Okay, so these are special cases. You know, the earlier FPT algorithms for these, so date back to, you know, 2007 and 2013, where Hamilcar and other researchers provide important progress for these. And here, when I'm talking about FPT algorithm, we mean the algorithm parameterized only by small submatrices. By saying parameterizing by small submatrices, I mean parameterizing by parameters that only depend on the small submatrices A, B, C, and D. And as you can see here, a summary. So we are using S to represent the number of rows and T to represent the number of columns, and delta, we mean the largest coefficient among all the entries, okay? And as you can see that both n-fold and two-stage stochastic, they admit FPT algorithm parameterized by small submatrices. And very interestingly, in recent years, there are a bunch of further improvement where nowadays we can, we are even able to deal with the generalized version of these where the small submatrices do not need to be identical, okay? They can even be different. That's kind of very good news. But unfortunately, for full block n-fold, it still remains as a core difficult problems in the field. So the best known result before was n to the power of parameters, which is doubly exponential. And in this paper, we kind of give an exponential improvement so that it's now become singly exponential. But I want to point out that the current running time in this paper is still not FPT. Okay, so it still remains as a major open problem whether there exists an FPT algorithm for this. Indeed, so I would like to also point out a little bit that because in addition to this n-fold and two-stage stochastic, I mentioned before, there are even more general block structured integer program that further includes, let's say, tree-fold and multi-stage stochastic and also others. But let me point out the fact that for all of these kind of block structured integer program, they are all trackable in FPT time, except for block n-fold. Okay, so I think that serves as another major motivation that why we want to pay a particular attention to full block n-fold in this paper. As I just mentioned before, okay, so one important contribution of this paper is on the improved algorithms. For, we provide an algorithm with better running time for full block n-fold. Besides that, we also make fundamental improvement regarding the combinatorial structure of full block n-fold, which, we hopefully later on it can lead to an FPT algorithm or W1 hardness. So we observe actually very interesting structural information for full block n-fold. So one important observation in this paper is that we realize that if we consider full block n-fold IP, then there exists some full block n-fold IP where the infinity norm of any kernel element, by saying kernel element, I mean a vector in the kernel where h times x equals to 0. Okay, so we basically show that there exists some full block n-fold where every kernel element has unbounded infinity norm. Okay, and by saying unbounded, I mean not bounded by any FPT value. As you can see here, it's dependent on n. So in contrast, okay, so all the currently non-tractable classes of block structured integer program, all of those, which admit an FPT algorithm, they are shown to admit a finiteness theorem, which states that the infinity norm or one norm of the kernel, they admit, any kernel element in those kind of, tractable classes of block structure IP, they can be decomposed into a sequence of kernel elements whose infinity norm or even one norm is bounded by FPT. Okay, so this basically shows a sharp difference between full block n-fold IP and those classes of block structured IP which admits an efficient FPT algorithm. And this is perhaps one of the major reasons that, for more than a decade, we are not actually able to get further improvement on the running time. In addition to this, we also observe a very interesting fact that if we further restrict C equals to 0, okay, remember that as I have shown you here, so the 4-block n-fold has 1 copy of C and n copies of A, B, and D. And if this C, the small sum matrix, is equals to 0, then it's very interesting that in this case, the 4-block n-fold, the kernel element admits a decomposition of thin kernel elements. By saying thin, I mean the kernel elements has FPT bounded infinity more. So which is kind of, very interesting here that the main obstacle actually lies in the fact that C can be non-zero. But there is, this is a good news, but there is kind of a bad news for this is that while we have such kind of a nice decomposition of any kernel elements into these kind of bases where they are thin, the problem is that such kind of a decomposition does not guarantee that all the thin elements, they are actually lying in the same offset. So the problem with this kind of decomposition is that these kind of basis element may lie in a different offset. And furthermore, if we restrict a decomposition in the same offset, okay, so which is captured by the so-called Graver basis. So if we further require that we must decompose the kernel element into elements that lies in the same offset, then even if C is 0, it could still lead to infinite, lead to unbounded infinity norm. Okay, so this basically means that we no longer have this nice property that each kernel element, the basis element is bounded by FPT. So we lose this fact if we restrict that they must lie in the same offset. And the fourth result, which is kind of contradictory, but not really, is that we show that, well, actually C equals to 0, okay? As we have demonstrated such nice property for these kind of special case is that it's actually without loss of generality. So indeed, any algorithm, okay, for the case of C equals to 0 carries over to the general 4-block n-fold IP. So that basically means if you have an algorithm that solves this special case where C equals to 0, you would immediately have an algorithm for the general case where C is not necessarily 0. And this is, of course, kind of interesting, but still, as I would point out, that this kind of result, still does not guarantee, still does not allow you to carry over the second conclusion, where you can decompose into thin element into the general 4-block n-fold, as we show that for general n-fold, if C is not equals to 0, you basically don't have such a nice decomposition. So these kind of results, as you can see, that our contribution part, they are seemingly kind of contradicting, but not really, okay? Great. And that's kind of all the result that we have, and hopefully so far, so I have convinced you the motivation, and I have also, mentioned about our contribution. And in the last few minutes, let me briefly talk about some of the technical ingredients in our paper. So hopefully it can give you a little bit flavor of why certain kind of, result is true. And here, I'm picking one of our result, which states that, which is the second result here, when C equals to 0, we show that the kernel element can be decomposed into thin kernel elements. And so here I would like to just briefly, give you a very brief idea about the general proof for this, okay? So yeah, so let's, to prove this, I mean, we are just using the very natural idea so let's take an arbitrary kernel element, okay? We try to prove that a kernel element can be decomposed into thin kernel elements. And the logic is that we want to show that if G is fat, okay, if G has, unbounded infinity norm, then we should be able to take out a part of G such that the remaining part is still lies in the kernel. And by iteratively repeating that, we will be able to derive a thin decomposition. So towards that, let's first start with G by writing the constraint H times G. Oh, okay, so let's write out the full matrix of H, and let's write G into n breaks where the first break is G0 that correspond to the first column C, B, 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 and then G1 to Gn corresponds to the remaining columns, okay? So let's just write G in such a form, and we know that H times G equals to 0. And now remember that G lies in the kernel of H. So G should also lies in the submatrix of H, where we just remove the first column, the first row, okay? And remember that if we remove the first row, the remaining part of the matrix belongs to two-stage stochastic matrix. And here we will be using a known result for two-stage stochastic integer program that any element that lies in the kernel of a two-stage stochastic IP, they can just be decomposed into a series of thin elements. So from that perspective, we should be able to write G into summation of G of K, where each G of K lies in the kernel of the two-stage stochastic matrix by removing the first row. And of course, these G of K, they do not necessarily satisfy the first set of constraints where you times C, D, 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 they do not necessarily goes to 0. And the very basic idea is that, well, individually they may not lead to 0, but if we, kind of merge part of them, maybe we get, 0. And of course, the basic idea just follows like this. So we have G of K, and the crucial observation here is that if we just look at the first break, okay, G of K 0, we realize that because the infinity norm is bounded, and because G of K, the first break, it has FPT number of entries. So essentially, you only have FPT number of different kind of first breaks, okay? So remember that G of K, it has n+1 breaks. So there could be a huge number of different kind of G of Ks. But if we only restrict our attention to their first break, G of 0, there are only FPT number of such kind of different kind of first breaks. So this allows us to group them. And basically, we will actually define a canonical vector, okay? So this requires some, it requires some careful selection, but let me just be simple and let's say we just pick some R of J, where R of J has one distinct GJ0, okay? So it has the first break, and then the remaining part is kind of, we pick some special remaining part to make it as a canonical vector. And by using the canonical vector R of J, we should be able to rewrite the summation G equals to summation of G of K. And here, this rewriting is just by simply like, we have the summation of G of K. And so let's group all of G of K, where they share the same first break, GK0. And for this, we subtract their corresponding canonical vector, and then we add back these canonical vector. Okay, so this is just a standard way of writing. And then interesting thing follows, as if you further look at the ice break of G of I, if you write in this way, you will realize that if GK minus the corresponding canonical vector, then in each ice break, it's actually lies in the kernel of the small submatrices A. And this allows us to further decompose this part into a summation of kernel elements, whose infinity norm is bounded, okay? And then, so if you realize this and plug in back this 0 times D, times G, remember C equals to 0, if you further plug back this equals to 0 and you expand it, it just takes some mathematical calculation. I'm not able to show you, to walk you through all the calculations, but if you believe me, okay? So you just write in this form and plugging back these kind of constraints, and then with some sorting of the terms, you can just rewrite this term into the following nice form, where here you have a matrix V, which of FPT size, okay? This V times a certain vector equals to 0. And this vector can be very huge, but V is of FPT size. And then, of course, that because this vector, it lies in the kernel of V, so I would be able to expand this vector, which might be very huge, into a summation of thin elements, okay? Here by GK of V, I mean the basis for V, this matrix is V, and so this has finite infinity norm. And here, the interesting part, or the critical part, I want to point out that if C is 0, then you have the very nice thing where the first few entries, as you can see, they are all multiples of n, which is nice. But if C is no longer 0, you lose such kind of property. And why a multiple of n can help? Because if you see here with some mathematical calculation, you realize that if the first part, all of them are multiple of n, then if any of lambda k is larger than n in the decomposition, I would be able to take out n from the lambda k. That's kind of the crucial idea that leads to the statement. Okay, so I'm skipping a lot of details, but hopefully this can give you a little bit idea regarding the proof. Okay, so I think I'm running out of time, so let me just quickly conclude my paper. So in this paper, we studied the 4-block enfold integer program, and we make important progress. So in particular, we show some nice combinatorial structure for the kernel space, for the kernel of these kind of 4-block structured integer program, and we also obtain improved running time of the algorithm. And of course, the major open problem still remains. So it's still, it remains open whether 4-block enfold admit an FPT algorithm. Okay, so thank you for your attention. Let me just